So our next speaker is Karen Alim from Max Planck Institute in Göttingen, and she will be telling us about an amazing organism, which you will discover soon. Thank you.
Thanks so much for this very cool symposium. I'm really enjoying being here, and also already the scientific discussions I had over breakfast and dinner. So I will tell you about fluid flows. Fluid flows are actually a key building block of life. Any higher organism has a fluid-filled network that's structurally important for the system to function. If it's the network of the hyphae of the fungus, the blood vasculature of a human eye, or the vasculature of a plant. I want you for a moment to zoom into the network and look at a single tube, because I want to have you think about the following idea. And the idea is that the flow through that single tube is itself information. The fluid flowing through the tube exerts a shear force on the tube wall. It comes with a pressure on the tube walls, and it may transport signaling molecules. So just by being there, the flows are information. And now if we're looking at them in the context where the tube walls are alive, a feedback can unfold. Say, for example, we have a tube, and the tube is responding to, say, the shear force by dilating. The tube dilates. It changes the fluid flow in that tube, and hence it changes the flow of information. Now we zoom back out into the whole network, and we make ourselves aware that the fluid flows throughout the entire network are inherently coupled. So if that single tube dilates, the entire flow throughout the network changes, and hence the flow of the shear force exerted throughout the network changes. And so you can see how a self-organization, just based on the notion that flow itself is information that may be read out by the active tube walls, is capable to reorganize the whole network morphology. So that's the key idea that I want you to think about throughout the talk. I want to investigate that feedback between flows and morphology. And there's a whole range of fundamental aspects that are important here. There's the notion of just how flows are controlled, which is a great stepping stone to understand what information is really being used in a biological system. There's the notion of adaptability, which is basically what I just described of how much does a tube respond to the information. There's the question of how does the topology of the network influence this feedback, or the hierarchy of bigger and smaller veins in the network. For today, I will use just a story on the flow control to investigate what is the information that is being read out by a biological system. And when you might not be familiar with the bright field images of the organism that I showed you here, but this is, as Thomas advertised, my amazing model system, which is called Phasarum polycephalum. And it's a slime mold. And here you see that it behaves as a giant cell. So this is a scale of 5 millimeters. So you have really a giant cell that in this case is foraging through an arena where we gave some bacterial food droplets. You see that this organism, it intrinsically has a network structure. And if we zoom into this network structure and we look at the dynamics, we see that the tubes are undergoing contraction. It's easiest to see if you zoom into one of the smaller veins. And that these contractions are actually driving the cytoplasm inside the tubes to shuffle flow forth and back. So what you actually have there is you have an actin cortex surrounding circumferentially these tube walls. And this actin cortex is undergoing rhythmic contractions. And these rhythmic contractions are displacing the fluid, the cytoplasmic fluid, and that's driving the flow forth and back. So most of the time, we're actually not looking at these very long timescales of the organism foraging around, which is, this is actually a movie that took about 3 days. But we're looking at much shorter timescales where the network is static. So that's on the scale of, like, say, that whole data set is going to be 3 hours. And so what this allows us to understand how are the flows coordinated across the network. So when I tell you that the actin is undergoing contractions here, then the question arises, how are the contractions coordinated across this network? And to do so, we took exactly that data set and we measured the contractions of the tube walls throughout the network. And we analyzed them, and then we can analyze, just map out the phase of these contractions over time. And if we do so, that's what you find. So what you see here is a traveling wave of contractions that's sweeping the entire network. What is pretty amazing is that we're here on a scale of 2 centimeters. So somehow, you have to take into account, like, a single vein is about 100 microns, 200 microns in diameter. So somehow the actin cortex over here is in check with the actin cortex 2 centimeters away to keep this peristaltic wave happily sweeping throughout the organism. What is additionally very, very striking is that this traveling wave actually scales with the size of the network. So here we have a network that's 2 centimeters. What I'm going to do is I'm going to take it out of the microscope, and I'm going to cut out a smaller piece down here, and I put it back under the microscope, and I take the data and analyze the contractions, and you see a new peristaltic wave that reoriented along the new longest axis, but it's still scaling with the size of the system. And you can go on and make it smaller. So you have a contraction wave that scales with the size of the network, matching network size up to 2 centimeters. So on the one point, this is a very efficient way of generating flows, which I can show you by just taking this network morphology and putting down this principle of having a contraction wave, where this is now a simulation, and I'm just putting down a peristaltic wave to look at the spread of particles, and you see that this is very efficient on shuffling particles around. I also want to use this observation that this is an efficient way of generating flows to introduce the notion that the hierarchy of the network actually matters. So what I did here when I put down the simulation is I cheated a little bit. I cheated in the sense that in the simulation, I was lazy and I assumed all tubes to have the same base diameter, which in reality is not true. They're bigger and they're smaller veins. And so Sophie set out and did the real job, which was, this is the same data set, it's just rotated by 90 degrees. So now we're going to compare the real network with the real hierarchy of bigger and smaller veins with the same one where I normalized all veins to have the same size. And we're going to follow again the spread of particles over time, comparing those two. And you see that in the one with the hierarchy, it spreads much further, and also in an asymmetric fashion. So hierarchy matters, and the organism even cares about the hierarchy by reorganizing its network morphology over long stretches of starvation. That's about 3 hours of starvation, to reorganize its network morphology in a way such that the transport capability of these tubes increases by 40%. So it really cares about having an efficient flow, and topology and hierarchy really play an important role in doing so. That was my detour to advertise that also these aspects are very important for understanding how information is propagated through flow networks. But I want to go back to this initial observation that we have these contractions being in check over a scale of 2 centimeters. And I want to go back to now ask the question, okay, I started with the idea that the tube has, the flow through a tube is information. So which of the possible kinds of information is the system really reading out? And to do that, Natalie set up to do the following experiment. What we do here is we're going to give a drop of sugar down here. And what we know is that a drop of sugar changes the amplitude of the contractions in this network. And so the trick that we did is we put down a localized stimulus. And so now we can follow how this localized stimulus really propagates into the network. And again, we'll measure the contractions, we analyze the contractions, and I'm just mapping out to you the increase in amplitude due to the stimulus. So stimulus is hitting now, and you see how the amplitude of contraction goes up here, and it propagates in. See, it takes the highways, it takes the big tubes first into the network. And so from that kind of data, I hope you can believe me that I can go in and I can measure the speed with which increase your amplitude propagates into the network. And so I have a speed, and I can now use that speed to compare the potential different mechanisms. Because if I look into, if I were to have like a shear force or a pressure wave propagating the information about this food stimulus, I can put in physiological parameters, and that gives me a range indicated here in red of the expected propagation speeds. In blue, I'm also showing the speed of action potentials in nervous and non-nervous systems, just as a reference because we're working as a biological system. So this is what we'd expect for shear force or pressure waves. And now we go in and we measure the speed with which the information propagates, and this is what we find. So there's always almost a gap of 2 orders of magnitude to what we'd expect from shear force or pressure waves. And it turns out that these velocities that we observe here are exactly the speed by which particles would be transported with the fluid flows. So it's signaling molecules being transported. That's the mode of transporting information. And so what we have here is actually even hijacking the fluid flows. So what we have is we have a stimulus that's being translated into some molecule that's transported with the fluid flows and increases the amplitude of the contractions. But the contractions, remember, they were driving the fluid flows. So I'm actually increasing the fluid flows again. So it feeds back. So it's hijacking the flows, making them faster to propagate that information into the network. This feedback cycle I can also cast into equations, and with these equations I can make predictions of, if that were true, what I would expect. And for example, one prediction that I made was that if that were true, that the propagation speed should be increased with the tube radius. So it's faster along bigger tubes and slower along smaller tubes. And that's again something that we could easily test in experiments, where we would take a network, and instead of putting a localized stimulus at the side, we put it in the center of the network. And by putting it into the center, we have bigger and smaller tubes all taking off from that signal at the same time. And this is just a chimograph along this magenta line over time. And the changes between darker and lighter gray show you the contractions. This big region in the center, this is where the stimulus hits. And you can really, by eye, see how the amplitude of the contractions, the difference between dark and white, goes up tremendously after this front propagating. And so we can measure these fronts, and indeed, they grow with tube size. Which confirms this thought that what the system is using to propagate information is some soluble signals that are transported with the fluid flows. So I want to hold on to that idea by now going back to we have these contractions, and the contractions are coordinated on the scale of 2 centimeters. Can we understand that? And to do that, I embarked on a theoretical project with a wonderful postdoc in my group, Jean-Daniel Juin, and we stated the following. We basically based our work on all this wonderful work that's been known about an acting cortex. And we just distilled it down to the essence, which is we have a tube shown in yellow, that's an active acting cortex, which has a viscoelastic restoring stress. And then it has a contractile stress that is controlled by calcium. So higher concentration of calcium will have the cortex contract. And also calcium, there are calcium channels, and if you have a stretch, you can have a stretch-activated increase of calcium inflow. And so you cast that into equations that you have calcium, like if the tube is stretched, calcium is flowing in, it contracts, and there's some recapturing of calcium, recycling of calcium that's described by these equations. Then we also take into account that when the tube is contracting, just by conservation of fluid volume captured by this equation, a contracting tube displaces the fluid, so the fluid has to flow. And the flow velocity of the fluid described over here is then a function of this viscoelastic restoring stress and the contractile stress. So far, this is what you could easily find in the literature, and this is just a few citations, and there could be a very long list. And now I'm adding one more idea. And that one more idea is that the calcium that's driving the contractions is transported with the fluid flows. So that's the only thing that I'm adding. And it's a simple enough system that I really only end up with 2 equations, one for the radius of the tube and one for the calcium. And for the time being in this theoretical adventure, I throw out that I have a whole network, just because it's going to make simulations complicated, and I will just think about a long tube, very long tube. So I can now investigate the dynamics of these equations. And it turns out that if you look into the phase space, you indeed, as a function of the parameters, you find a region where the tube is undergoing oscillations. And it's also the regime where you would expect yourself to be matching your physiological parameters. So what that means, being in this oscillatory regime, is now that if I look along my tube over time, along the tube over time, this is mapping out the flow along the tube, you see this traveling waves of the fluid flowing through the tube. So we're done, right? But we're good theoretical physicists. So we're good in a sense. What we do is we have parameters in our equations, and we make sure that we match these parameters as closely to observations of the fluid flows, the amplitude of the contractions, and physiological knowledge about the elasticity and so on. So if we do all that, we find that the systems of equation has an intrinsic wavelength that is 7 millimeters. That's much shorter than the advertised 2 centimeters. So something went wrong. So what does it mean if you have an intrinsic wavelength of 7 millimeters? Let me explain to you. So if this is now rescaled in terms of this intrinsic wavelength. So if I have a tube that's in length half the intrinsic wavelength, that means that the pattern self-organizes to be exactly half the intrinsic wavelength, matching the size of the tube. But if your tube becomes bigger than the intrinsic wavelength, so this point, the pattern falls apart, and it falls into all of a sudden generating 2 or 3 or 4 of these waves into a single tube. Which means that you don't have any scaling of the size of the wave matching the tube length if you're above the tube, the intrinsic wavelengths. This is true for a closed tube. But we also investigated loop tubes. And all of a sudden, we did find in our simulations data where it did scale. And so we went in and we investigated. And we realized that we could have this scaling being very robust if we take a small tube and we slowly grow it and have the pattern adapt during that growth. And all of a sudden, the wave size can scale with the size length of the tube up to 7 times the intrinsic wavelengths before this pattern breaks down. Look at there's the closed tube as well. For the closed tube, this does not happen. For the closed tube, whatever we'd expect from our theoretical predictions is still true. It goes up to 1, the intrinsic wavelengths, and that's stable. This scales. 7 times the intrinsic wavelengths gives a new scaling limit of 4.7 centimeters, and we're all on check. The key essence that's driving this very unexpected scaling is the fluid flow. So you have additional fluid flow due to the looped topology of the network that is able to generate this long-range scaling because it's transporting the fluid flow. You can change the viscosity of the fluid in the simulations, which would decrease the length scale on which particles are being transported, and your scaling breaks down earlier. So I showed you a story of how, looking at the question of flow control, we can identify how information is transported with the fluid flow and feeds back on the morphology of a transport network. I showed you that flows scale with network size, and that we can have this long-range coordination via the transport of signaling molecules with the fluid flows. This is just one aspect of this feedback between flow and morphology. And I'm very excited to investigate the role of adaptability, how the local dilation of a tube changes transport, the flux, the absorption, the supply of a network in itself, and how it can generate a self-organized optimization of the network. I'm investigating the role of the topology of the network, how it can stabilize fluid flows, how loops can generate overall larger flows. And I'm also especially excited about the role of hierarchy in the network, because the hierarchy of bigger and smaller vein actually can be changed by stimuli. So basically the pattern of bigger and smaller veins stores information about previous events, which would allow you to not only store the information, but also read it out to anticipate events. I'm studying all these notions in Physarum, but I do have in context that we should desperately understand the physics of flow networks. And I'm being very selfish in doing so, and I'm looking at myself, because we as humans, we're basically filled with tubular networks. There's the vasculature. Our brain is basically a porous system where we have cerebral flow. The bronchi, the kidney has a nephron network. There's our esophagus, there's the intestines, there's the lymph, there's a tumor system. I could go on. It's intrinsic to biological systems that you need these transport networks. Not only to biological systems. If you think about self-organizing porous media, building smart materials, synthetic organ printing, understanding the interplay between flow and morphology is crucial. With that, I would love to, first of all, thank my team in Göttingen and you for your attention. And also, if you got excited about the fluid physics of life, there's a wonderful workshop coming up in Dresden. Thank you.